This is chapter 17, Basic Chemistry Pearson. And this chapter looks at organic chemistry, and as always in these work sessions will not be on the full lecture. Alkanes, we'll talk about alkynes, alkynes, polymers. We'll talk about some alkenes as well, which is probably what this should be. Aromatic compounds, alcohol and ethers, aldehydes, ketones, carboxylic acid, esters, amines, and at the end of this, what you're going to be exposed to is the functional groups in organic chemistry and why they do what they do and what they look like. The extent to which you have to give this back to me on the exam is yet to be determined. We will do that during the actual work sessions. All right? Here we go. Organic chemistry is an inorganic compound was a substance that composed of minerals. An organic compound, something that came from an organism, thus use the word organic. So here's the bottom line. Organic compounds here we talk about are the substance of life. Inorganics don't. So if you to identify an organic compound that has lots of carbon and hydrogen, it's organic. Carbon, hydrogens, few oxygens, it's organic. Carbon, hydrogens, and a few nitrogens, it's organic. Carbon, hydrogens, and a phosphorus every now and then, or sulfur or so, it's organic. So for the most part, it's this compounds of life: carbon, hydrogen, and oxygen. Okay. So this definition, the first one here, is how the author chooses to describe this. I don't. So keep in mind, we talk about, this is what we really start to talk about here when we talk about organic compounds, okay? All right? And for the most part, the organic compounds are molecular compounds. All right? So that's the type of compounds you have. You will have some that have ionic character, and you, in fact, do have them. But for the most part, they'll be molecular compounds, and occasionally they will have functionality that imparts ionic character. Does everyone follow that? That's organic. Okay, molecules that in biological systems they will have functionality in parts that has ionic character, and ionic character is very important for transport through the body. That's why organics are very. Ionics are important in the body. All right, occurs in nature. Fuels, shampoos, cosmetic, perfumes, foods, etc. There's foundation of our understanding of biochemistry. All right, so you'll get a little bit of exposure to that. Hydrocarbons are organic compounds that contain carbon and hydrogen. But I really do. This is the definition I expect you to just flat out know. All right, hydrocarbons are organic compounds that contain carbon and hydrogen. That question will be on the exam. Okay, all right. I expect you to really know this one. All right. Anybody missing that one, I'm just going to stop reading you the rest of the exam, put a big X on it or something. Hydrocarbon, it might be the first one on the exam, as a matter of fact, just to see what happens, all right? Propane, C3H8, is an organic compound, where sodium chloride is an inorganic compound. So if it's on the periodic table, composed of simply, 2 or 3 or 4 material from the periodic table other than carbon and hydrogen, it's likely to be inorganic. Everyone follow that? On the periodic table, other than carbon and hydrogen, it's likely to be inorganic. If it's small portions of carbon and hydrogen, and for the most part, everything else on the periodic table, then it's inorganic. Okay? That's how we differentiate it. In the class of organic compounds, sorry about that, in the class of organic compounds, we have what's called alkanes. They do not have any unsaturation. They're only carbon and hydrogen and alkanes, okay? Ethane, propane, butane. You recognize these, right? Propane, that's what you just did on the 4th of July around your barbecue grill. Butane, that's for those who choose to smoke and have a cigarette lighter. And so they have number of carbons, and those carbons are from one to many. Okay? If it's a polymer, it's many. Okay? So it's a continuous chain, but that chain may be branched in some fashion. So alkanes, here's the bottom line for alkanes, they are completely saturated. So alkanes are completely saturated. That's a key term to use. Okay, so alkanes are completely saturated. And here are some examples that we show you here. This is methane. Methane, covalent bonds of hydrogen directly directed towards the corner of this tetrahedron. In other words, what you have is a tetrahedron shape, and you have carbon in the center, and these hydrogens are evenly spaced around at about 109 degrees. And this 109 degrees is so that it relieves any stress on it. It's an ideal structure for this. And these are several different depictions of it. So we have methane here. Three-dimensional and two-dimensional representation. Methane, all shown here, and these are all different types. And they're used for different things. This, here, space field model really shows you where the electron densities are. This shows you the space, and this is a simple cartoon for seeing it. And this was being drawn way before models were built, consistently built. They were being built in, but not consistently built. And this is simply a drawing, and this is a shorthand notation of it. And so we do that. So this is methane. It is an alkane. Methane is an alkane. Here we show you the names of all of these are shown here on this table. This table 17.2 and this 17.2. And what you discover is that they have these names: methane, ethane, propane, butane, pentane, hexane, heptane, octane, no name, decane. I expect you to know that methane is C1, propane, because it's something you're familiar with, is C3. Okay, so if you see C1 methane, C3 is propane. And how about we know octane, because that's in fuel, C8. Those are the ones I would expect you to know, okay, at this point in the semester. So if you know methane, C4H4, so memorize this one, memorize propane, memorize octane, okay? All the others I would give you on any exams or any questions we have, all right? So we know methane's just basically gas, natural gas. It blows out of the earth from fossils. It's the low boiler. Yeah, low boiler in methane, most volatile in fossil fuel. Excuse me. It's the low boiler in fossil fuel, most volatile. Propane is what we use in our tanks for barbecue grills, and octane is in the fuels we burn. And these show you pictures of it. Structural isomers of C4 have the same number of types of atoms, but are bonded in different ways. That's what an isomer is. It has the same count. You count it, you're going to just count the carbons. Okay? And if it's an alkane, all it's going to be is carbon and hydrogen. So everyone follow? You will always know an alkane because it will always simply be carbon and hydrogen and no double bonds. Okay? Carbon, hydrogen, no double bonds is an alkane. This alkane is what? Butane, right? And this is called isobutane. Okay? This is in a cigarette lighter. This is not. Okay? You've seen this before. This is something I expect you can do, right? You've seen here. This is propane plus oxygen. You know how to balance the equation, right? And release energy, endothermic, exothermic. Yeah. What would the sign be on this exothermic reaction? Negative or positive? Yeah, negative. Get it? Okay? So you ought to keep that in mind. Those type questions I could ask you because we've done this before. And I would use this as my example of what type of reaction is this? Everyone know what type this is? Combustion. Very good. So this type of question I would take a look at this one because I've asked you to memorize methane, propane, and octane. So I would take a look at this and be familiar with it because it's either going to be methane, propane, or octane. It's a combustion reaction. I get to ask you a lot of questions from one simple organic reaction. Does everyone follow? Okay. So I know you know how to balance the equation. I know you understand exothermic reactions. Okay. And you know it's octane, because I would say propane, and you would have to write it out. Does everyone follow that? All right, at this point, I don't expect you to write it real pretty, okay? All right? And for goodness sakes, if you forget the number of hydrogens, please don't forget the number of carbons. I may be in a very good mood when I grade it. Propane is C3. At least, okay, if you get that far, at least I'll consider, okay, maybe they dozed off a little bit and forgot to write the H's. But if you don't write a C3, then that tells me you didn't remember it at all. C8 is octane. Okay? Very good. All right, parafilms has a lot of carbons in it. Waxy, it's 18, or more. The waxy coating on the fruit and vegetables is composed of solid alkane to resist moisture, so it doesn't start to rot as fast, okay, and brown. As a matter of fact, one of the tricks for vinegars, you guys, anybody use that trick to put stuff that browns vinegar? Yeah. That's an organic acid. We'll talk about it later, but it's an organic acid, and that actually just keeps the water from attacking those surfaces. Okay. But in this case, this is a polish. You just polish the apples, and they look really good. That's why, if you go to the store and they kind of bite the apples, particularly in the really high-end supermarkets, they polish them so they look really beautiful. When you look at, oh, this is a great apple. It's going to taste so good. And still bad apple, right? But a polish on it. Okay? So that's one of the uses. So there you have it for alkanes. That's what we expect you to be familiar with when it comes to alkanes, that they're single bonded, carbon and hydrogen only, right? And we expect you to know at least 3 of them, and we expect you to know the combustion reaction is an exothermic reaction. It's burning fuel, okay? Burning fuel is always exothermic, and that gives it a negative. An alkene, what's the difference? Take an alkane, add a double bond. That's it. So if you see an alkane with a double bond, it's called an alkene, okay? All right? And I'll tell you in advance, an alkyne is going to be triple bond, just so you have it when we come to it. So you have an alkane, right? No double bonds, right? All single bonds. An alkene would have at least one double bond. An alkyne would have one triple bond. Okay? That's how you know them all. There you have it all. Do they undergo similar reaction? Yes, they do. Do they undergo combustion? Yes, they do. Similar type balanced equation? Yes, it does. And what type of reaction is it? It's exothermic, which means the heat given off is going to be negative, therefore you can use it to fuel your home. Okay? Like okay? Here we have, ethine, okay? This is ethylene. You're going to learn about, I think we're going to have acetylene in here somewhere. So, there you have for alkenes and alkynes. That's the difference. Everything, for the most part, everything else is similar. We name them, instead of ethane, it's called ethene. Instead of ethane, it's called ethine. We just name it with the Y-N-E. So everyone see that? You got it? So if you understand alkanes, the rest of it just follows by remembering ene. It's ane, ene, and ine. Okay? All right? So you have anes, enes, and ines. All right? The type of question you might see on an exam would be, I would have an alkane drawn, an alkene drawn, an alkyne, and you would tell me whether it's alkene, alkyne. You get it? Okay? You'd match them up. All right? So here we show you the classification of the organic compounds. So you know alkenes, you know alkanes. Why? We know alkynes, right? You just simply look for the double bond and triple bond, okay? And we really would like for you to know an alcohol. If you see an OH functionality, it's an alcohol, ethanol, which is used for several purposes. Used for medicinal purposes, okay? Right? And it's also used in the corn for fuel. So ethanol. So I expect you to know ethanol. This one, okay? OH functional. Then we have carboxylic acid, esters, amine, and amides. We're going to come to these a little bit later. And this is your fishy odor. So when you smell that really fishy odor, that's called an amine. You get that amine odor, okay? And there we have it. This is vinegar, okay? Acetic acid is in vinegar. Okay? Acetic acid is comes from fruits. So, this is a fruit acid. It is also, acetic acid also used as a buffer along with the salt. You see, right? The sodium salt of acetic acid is a buffer. And then we have these really long molecules, very large molecules that most of us are sitting on and playing with called polymers. If it's a plastic, it's a polymer. Here you go. Plastics are polymers. True or false?
True.
There you go. Please don't miss that. Okay. Long chain molecules found in nature, cellulose in plants, starches in foods, tortoise shells, rhinoceros horns, also made synthetically, for example, polyethylene, polystyrene, Teflon, and nylon. These are the plastics that we enjoy. And these are also the plastics, unfortunately, are contaminating the world. Okay? If you really want to see an interesting video on contamination, type in BBC Plastic Island or something like that. It is a really kind of, for those of you who care about wildlife, it really kind of gets you a bit, okay? But it is the nature that we created. This is why people like me started carrying, as painful as it is, started carrying bags in his truck. Yeah, I do that kind of thing already for going in the supermarket so that I don't take any more plastics. It's kind of my giving back, says, yeah, I was part of helping create a lot of that trouble. So it's kind of my way of saying, gee whiz, do something right for once, okay? And do something good. So my point here is polymers are a part of our society. They will not go away. The question is, how responsible are we being with them? That's the real question and issue that we face. All right? All right, so are made of synthetic, so we have these. So we have natural polymers and we have synthetic polymers. They are exactly the same when we make them synthetically. There's no difference in a natural polymer and a synthetic polymer. But there are some natural polymers that we can't make. And there are some synthetic polymers that don't exist in nature. Okay? Right. Here we show you an example of how polymers are made. They're made from these starting units. One unit adds to the second, adds to the third, and that's called polymerization. So we get polymerization, and we get this really long chain, and we're able to stretch it and play with it, sit on it, tap on it with our iPads, the whole bit. Okay? All right. So we get the polymers made, and this is the world of plastics. This is slide number 14 in this particular lecture. Here we show you some examples. Polyethylene, polyvinyl chlorides used. Polyethylene is used to make your bottles, and actually, And PET is also used to make most of your drinking bottles are PET anymore. Okay, but polyethylene is used to make several of them. Polyvinyl chloride. This is a water hose that when I was growing up, we just drank from the water hose. Yeah. Nothing like a refreshing drink of water from a water hose. Yeah. Okay, I may have mental issues because of it, but I'm still alive. This may explain me, right? Yeah. Okay. PVC, polypropylene, and things of that nature, nylons, etc. This is Teflon's used here, Saran. This is Dow's big winner. And polystyrene's Dow's big winner. And this used to be a huge winner in terms of sales for Dow when McDonald's was using it, the leading fast food restaurant in the world was using it. But some environmentalists, when they were looking at trash around the world and looking out in the oceans and landfills, Guess who kept popping up? Ronald McDonald, all over these things. And the publicity was really bad against McDonald's. So that's why they went to paper several years back, probably before at least maybe one or two of you were born. Okay, but that's why they went to paper, because styrofoam is not biodegradable. Okay, and that's why. So there you have it. These are examples of synthetic polymers. They have a lot of use here. Get the Teflon skillets. You can get them QVC, or you can just roll the Ollie's on State Street. Anyway, you can get them anywhere. Okay, anymore is the point. Here, these are examples. These are the codes with the plastics, and these codes are used for recycling. Let's see my next slide. Okay, I have it. All right. You can identify the type of polymer used in manufacture a plastic item by looking for the recycling symbol arrow in a triangle. So you tend to look at those on plastic. So it's kind of a thing to do, and it helps you decide how to recycle it. There's an argument between whether the white caps on bottles, plastic bottles, or drinking bottles, like you buy water bottles, whether they should be sent together or separate. I tend to do it separate. They actually do have a different code, but it's kind of one of those arguments that goes on. In some cases, in some areas, they will not take time to take those off. They'll simply send it to the landfill then, and see it instead of recycling. Okay? They don't have the manpower to do it. They're not going to pay for cheap labor to do it. It's the way it is. Okay? So be aware of that when you're sorting your recycling. So here we have PET 1, 2, and you'll see what these mean later. I think on the next slide. PVC. PVC has chlorine in it, so many times it will be segregated separately because when it's burned, it gives off chlorine. This is also why it can't be reblended with some other polymers because of chlorine content. Okay, so this tends to be segregated a fair amount, and then some of these, the densities are so different that when you try to process them, one's floating, one's sinking, so they'll segregate by that as well. But this is what we have here. Okay, polystyrene tends to stand over to itself a lot. So this is what they mean here. So for low density polyethylene, low density means it's not as dense. When it's not as dense, that means you don't put gasoline in it, folks, because it doesn't have the density. So higher density is for things you want to really keep safe and tough. Okay? And you don't want things to leach out or what you would call melt. Okay, when you put it in, you say it melted. And exactly melted is basically just destroying the polymer structure. Okay, and you'll occasionally say it melts. Melting is when heat sees it. Okay, so that's decomposition. So we have that. So that's the difference in these plastics. These low density tend to be branched polymers. High density are unbranched. So they stack really well and make it really dense. And this is a milk, should be somewhere over here. Milk, yeah, shampoo bottles. Yeah, over here. And here, these are bags that you stretch. Here, we know PVC now, garden hose, waterproof boots, shower curtains, etc. It's a special class. And then we have here polystyrene. You know that. Insulation, right? Polypropylene, here we go, yogurt cups, creams, carpeting, here's a lot, and PET, soft drink bottles, clear food containers. These are things you see a lot in the packaging in the fruit section at the supermarket. Polystyrene is also what your dads and your grandpas, when they go to the store to buy a CD, yeah, because they still want the case, right? You only do downloads. I know, it's ancient history, but that's why grandpa and some of your parents still go when they get the CD case. It's polystyrene. That's also if you go in like Macy's, a lot of the stands that you see around there, polystyrene, because they look so beautiful, pristine. Okay, some of the lower-end stores will use polyethylene and Yeah, we'll use polyethylene because it's cheaper. Put those up. Okay. I think with polystyrene it'll scratch easily, but in Macy's you just dust it and you keep going. Okay. So there you have it. Okay, so so let's talk about some of this chemistry a bit further in terms of how it relates to foods and health. Chemistry link, hydrogenation of unsaturated fats. This is slide number 19 in this lecture. The unsaturated fats in vegetable oils are converted to saturated fats to make a more solid product. So in other words, we'll go from something a bit softer to something more solid. Okay? This is called unsaturated, and with many double bonds, it's called polyunsaturated, which you've heard before. And these are your saturated. Okay? These will decompose faster than these. These will decompose and give you odors, where these won't over a short period of time. Okay? That's because it cleaves this bond and it makes a volatile material. If you can smell it, that means it's volatile, by the way. If you smell it, it's volatile. Got it? Okay? So that means it's a smaller molecule. Volatile molecules tend to be smaller organic molecules. All right? So these fall apart, make really rancid odors. That's actually, anybody bake and leave your butter out?
Mm-hmm. You gotta leave real butter out.
Yeah, you leave real butter out, you're decomposing it to get the rest of the flavors and the rest of the compounds that make that cake taste a lot better than the one.
You want everything to be the same temperature when
I'm sorry?
you want everything to be the same temperature when you do it. So you leave your eggs out.
Yeah. Okay. There you go. You bake
That's
it.
the chemistry of baking.
There you go. You bakers again. All right. See, I'm pretending like I know something about baking. Okay. But occasionally, what would happen? People would have a cake, right? And they'd say, "Tastes different," or "It's different. It's doing something different." And for some, they would leave the butter out like days. They just leave the butter out. Okay. Yeah. And they bake with it, and man, they swear by it. I've had cakes that've been out. I don't like taste real different, but I'm convinced I was sold on it with my grandma. Okay, my grandma said her cake tastes good. I always say, "Grandma, it tastes good." Okay, and that's because I leave my butter out. And I go, "Oh, good news, Grandma. Thanks." Okay, you get it? But this is what's happening. It's decomposing. Okay, and it creates slightly different materials in the butter than when it doesn't decompose. All right. All right. So there you have it. For alkanes, for simple alkanes, alkenes, and alkynes. Let's talk about benzene, an aromatic compound. There you go. It's aromatic. We have benzene. It's a 6-membered electron ring, and this is what it looks like. Okay? It's extremely stable due to resonance between the double bonds. It's found in many compounds with fragrant odors. Thus, benzene compounds are called aromatic. So you'll have this ring, and this ring is derivatized or has other groups on it that makes it give off certain aromas. Okay? And so we draw like this. So be aware of benzene. I would simply ask you to be able, I would have on there circle benzene. Got it? And you circle benzene. And it will be really obvious to you, okay, which one's benzene. Okay? If it's not, that means you missed my lecture today and you didn't read it. But benzene's going to look like benzene. It's going to be really kind of one of those obvious things, okay? It looks just like benzene. All right, so now here are some derivatives of benzene. So these are derivatives of benzene. So does everyone see benzene in this? You know what it looks like now. Okay? And these are derivatives to show you the fragrances from these grasses and flowers and from nature. And so this is what you're smelling. Okay? The aroma and flavor of herbs arise from these. That's the bottom line. Okay? And people like thyme for some reason. Right? Anybody, what you bake with this stuff? Is that what you do?
What?
Thyme. Is that
Time.
You bake in it.
Cook with it.
Yeah, put it in leaves. It's like the leaf you put in food. Yeah, I don't cook. I just teach this stuff. I don't cook.
I can't cook, but I can bake.
Okay.
And I do not use time.
Okay. There's people that make soups,
Savory things like chicken
soups and broths and all.
Your
Yeah.
turkey.
Yeah.
Turkey. Yep.
Yeah, I've seen it used.
I know it goes on turkey.
Okay. So I just know the chemistry. I don't cook at all. I'm gonna make one dish. That's it. Okay, here we go. Notice this again, benzene ring. Okay, it's a derivative of benzene. This is called toluene. Okay? And the further derivative of toluene is TNT. And it has a lot of potential energy because of all these double bonds. So if you draw out the full Lewis structure, which I'm sure you are capable of doing by now, if you draw the full Lewis structure, you see all these double bonds here, here, and here, and 6 here. And it has a lot of potential energy. That's TNT. Okay? All right? Endothermic or exothermic decomposition? Exo. Positive or negative? Negative. Very good.
Are we going to have to draw the Lewis structure?
No, no, you won't. None of this. Aromatic compounds are common in nature, and so we show you some others here. And then we show you benzene ring is found in pain relievers such as aspirin, acetaminophen, ibuprofen, etc., vanilla flavors. So here, this is ibuprofen. And this is why some of these medicines were developed. It started with aspirin, which came from really a willow tree. And what discovered was that the derivative in the stomach was what was really the pain reliever. And so Bayer said, gee, why don't we just make it independent of that process happening in the stomach? And they did, and they patented it. And they own the world patent to aspirin. But from this structure, synthetic chemists were able to look at it and say, gee, you know what? This is more water soluble, and it actually irritates the stomach, causes a little bit of nausea. They said perhaps we'll make it a little bit more fat soluble, where it doesn't, and move this over a little bit where it's not quite as acidic on the stomach. Okay? But we can still get the pain relief from it because it has the basic structure to do that, to affect that. So this is why ibuprofen is used a lot for inflammation, things of that nature. Okay, it's an anti-inflammatory because it's fat soluble. And here, acetaminophen was simply developed to relieve that nauseating feeling of aspirin, but give you the same impact. Of these, aspirin is the only one that's a blood thinner. So when someone's saying, I'm going to take ibuprofen to thin my blood, acetaminophen, that's not going to happen. Aspirin is the only blood thinner of them. All will relieve pain. This is more water soluble, but with nausea or irritation on the stomach. This is more still water soluble with less irritation. This is fat soluble pain relief. So it just depends on where your system is and what you can tolerate and where you want to get it. A lot of athletes do ibuprofen a lot. Okay. And this is vanilla. And alcohol contains hydroxyl. That's it, folks. All right, it's bonded to a hydrocarbon chain. So if you see a hydrocarbon chain, an alkane with an OH on it, that's called an alcohol. I expect you to know an alcohol. A phenol is a benzene derivative of the alcohol. Ethers have 2 carbons that are attached to the oxygen atom. Okay, ethers. Okay? So, what do we know? Alcohols. This is oxalic acid. Okay. This alcohol is derivatized or oxidized, actually, to oxalic acid. Okay? So it undergoes oxidation, and this is used in antifreeze, ethylene glycol, used in antifreeze, heating and cooling systems, solvents for paint, inks, extremely toxic if ingested, and has a sweet taste attracted to pets and children, and this is why you want to make sure that stuff stays out of the way. And I'm sure at some point you watch the LMN movie and discover this antifreeze, right? It's you know they just put it in their punch on the during the movie, and they couldn't taste and didn't affect the taste, right? You've seen the movies. Should I say more? Okay. So that's antifreeze. It's an alcohol, actually. Okay, a glycol, ethylene glycol to be specific. Phenols are found in essential oils in plants. So you have these essential oils in plants and you find these phenols. Why the phenols? They're aromatic. Okay? All right? If they're aromatic, they have a benzene ring. Okay? So here we show you several examples, vanilla, etc., etc., etc. Okay? So we have all these different ones, and there are many, many more. We won't go through the details on these, but suffice it to say that phenols are aromatic compounds that are found in essential oils. It's the benzene ring. Everyone see the benzene ring again? Okay? All right. There is a phenol found in oils, etc., nutmeg, thyme, cloves, and vanilla. Okay? Bisphenol A, which has come on attack because at one point it was used. It's come on attack because at one point bisphenol A polycarbonate was used in baby products that they chewed on. Not good. Found to be a health issue with that. So bisphenol A, many are trying to get away from it, but the uses of it are so widespread and so useful for the product where they are. And I just put precautions on it by saying it contains BPA. Bisphenol A is used to make polycarbonate. It's probably big bottles. I'm talking without reading my own slides. Polycarbonate baby bottles. Okay. So many people don't like this and won't buy them. Won't do it because it's coming to scrutiny in terms of whether or not it's helpful or harmful. Washing polycarbonate bottles with certain detergents or high temperature cause small, here it is, amounts of BPA to leach from the bottles. Get it?
Well, is that why they say don't leave cases of water in your car because they will make the BPA come out of the plastic?
Yeah, for those, if it contains polycarbonate, but the other plastics don't contain it. But all,
Because you can buy reusable bottles that'll say BPA free,
right.
But mainly cases of water do not say that.
Yes, but many of the water bottles today aren't polycarbonate.
Okay.
They're usually PTE or polyethylene. Now, that doesn't mean, however, that other leaching material won't come out. That's what I want to get to. Even if it's not BPA, okay, certain plastic will eventually decompose, okay? And if it's plastic for a reason, get it? And some plastics still contain what's called plasticizers, which are the agents that allow them to remain flexible. And so that's why they do that. Some of it's a little bit of fear tactic for others to sell their products, but there are some leach agents in some certain bottles. Mostly polypropylene, polyethylenes for the most part. For the most part, and I have to be real careful with saying that, tends not to happen. But many err on the side of precaution, okay? Because you occasionally get, I would use the term, cheap product.
Well, this between death and surviving because I have water in the car. I'm going to drink the water, but I'm not going to drink it on a regular day.
Yeah. But for the most part, there's no bisphenol A isn't used in most of your water bottles. I don't know of any newer water bottles that use BPA because it fell under this scrutiny. Yeah. So that's the concern. It mimics estrogen. Okay. So be aware of that. Let's see. So here, then we have what's called carbonyl compounds. These carbonyl compounds have this carbonyl group, which is a C double bond O. Therefore, it is polarized in the direction of the oxygen. We have ketones, and they're attached. We have aldehydes, and your formaldehyde is your star winner here. And we have other ketones, acetone, which is in your nail polish remover. Okay, and I don't know if we're going to talk about esters or not. Hopefully we will. If we don't get to esters, I'll say it now. You have ethyl acetate, which is an ester is used in nail polish remover. So you have acetone and ethyl acetate is there, and so that's why it removes your. It's a paint thinner or polish thinner. Then we have carboxylic acids. Carbon atom has a carboxyl carbonyl group attached to an OH. This is what it looks like. So this is the carboxylic group and the hydroxyl functionality. Example is propionic acid, or you are familiar with acetic acid, right, from vinegar. Vinegar is acetic acid. That's the kind of thing I'd like for you to know at least when you leave this class, right? Acetic acid is vinegar. Okay? All right? Here are some other examples of acids, and you use them for those of you who cook and put vinegars and stuff on salad dressings, etc. Sour taste of vinegar is due to ethanoic acid, acetic acid. What about metabolism? Here is what happens during glycolysis, and this is an important process. Glycolysis, a molecule of glucose is broken down into 2 moles of pyruvate, or actually it's carboxylate ion pyruvate. So you get pyruvic acid from this. And this is something I like for you to be familiar with. Glycolysis is an important process for doing that. And that's why this is what happens when runners run, for your breathing. Okay? It's an important process. Okay, for breathing, for respiration. So that's glycolysis. And so we take pyruvic acid, and it undergoes reduction. Here we get lactic acid, which you hear athletes talk about, and they're sweating, they're getting all this. Okay, so athletes are well familiar with this. Okay, or it's ion. And the ion is going to be something like sodium or potassium. Okay. Or some of the ion, but likely sodium or potassium ions. And by the way, this is for Gatorade, which is developed at the University of Florida, was developed to restore electrolytes to help this process as part of this regeneration process. They say, or it's lactic acid ions. Gatorade is developed to make sure you have enough ions in your system. And the athletes there at University of Florida proved that. Esters, in a reaction called esterification, esters produced when a carboxylic acid and alcohol are heated with a strong acid catalyst. So a catalyst does what? Lowers the what? Activation energy. Gives you the same product, but it gives you to it a bit faster and a lower energy cost to do that. In this case, we get these esters. We get esters, therefore we get fragrances. Okay? We get banana oil and all banana odor and whatever, peach, etc., etc. So you get these aromas, and here we show them to you: fruits and flavorings. We have, what do we have? Pears, polyethanoate, pentyl, ethanoate, banana, ethylbutanate, pineapple, apricot, etc. So simply by changing these groups, we can get a different fragrance, a different flavor. Okay? And in some laboratories we do this. I don't know where we're doing this or not in this lab. But this is always a fun lab to do. It just smells like the fruit market. Okay, when you do it. So esters, right, are the organic compound that gives fruits their flavor, their aroma.
So is that what they add to orange juice to make it orange juice? Flavor?
Yeah. It would say artificial flavoring. If you see that, yep, they've added one of these esters. That is correct. Yep, artificial flavoring. It's the same chemistry, just not natural. And therein is when you have the people who do it naturally, that's their argument, right? Ours is natural, they're synthetic. And the synthetic people will say, well, ours is just as pure as yours. And they'll say, no, it's not. Because it's possible that there's that asymptotic amount of some byproduct in there. And that's possible, but unlikely, but it's a good argument for marketing purposes, right? If you get it natural, you don't have to worry about that asymptotic amount of that impurity, okay? It may be out 0.00001, but you say that might be enough to affect me. So yeah, but it's artificial flavorings. That's what they are. Some guy.
They're usually cheaper.
Yep. Yes, they are for the reason I just described. Because to get it naturally, you got to take up a lot of materials, a lot of vegetables and fruits and etc. And to process that to make sure it stays that way. So that's what you're paying for. Plus you're paying for a bit of the marketing hype to go with it. But yeah, these are cheaper. So this is why you want to make sure, by the way, that people know they're safe figs. Because there's guys that are doing your artificial flavoring. You wouldn't want them to miss on this, right? When it comes to your sick figs and putting it in there, right? They say, well, what's the impurity in there? Oh, it's about 0.22, Bob. It should be, and he said, but it should be the 4 sig figs. You get it? And Bob said it was 22. You get it? It should have been 22.001 or something. You get it? So you got to know your sig figs, folks. All right, here we come. Alkaloids are physiologically active nitrogen-containing compounds produced by plants. Basic compounds. Aha! Anesthetics. And that's what I like for you to know. The class of compound used in anesthetics and antidepressants are called alkaloids. I like for you to know that. This is slide number 34. That's what I like for you to know. Okay? They're called alkaloids. That's kind of an important thing to know, particularly for your major. And this is an example of an alkaloid, nicotine. Whether it's through tobacco or something else or vape or whatever, nicotine's nicotine. It's a stimulant, increases the level of adrenaline in the blood, which increases heart rate and blood pressure. So you do nicotine, blood pressure goes up, it's chemistry, it's going to happen. So, well, I'm too chilled, I'm too relaxed, Okay, yeah, I hear you, but this is chemistry. It's going to do it. Okay? It's addictive because it activates pleasure centers in the brain. And it activates it more than simple caffeine. Caffeine is a stimulant. It gets you up, but it's a non-addicting, although that can speak for yourself, right? Where's my cup of coffee, as a matter of fact?
Yeah, this is my second one.
Right.
So 10 minutes before.
Speak for yourself. You get it? Does everyone get it? I should make lighter that, but that's the key. These stimulants, that's what they do. That is the nature. It activates the pleasure center of the brain, and pleasure drives it. That's brain chemistry. Okay? That's just what it does. And when you hear people saying, he's out of his mind, he really is. His brain chemistry is shifted. And that's what's happening. Okay? And the brain chemistry is shifted, which means the hormones are shifted, which mean the messengers, hormones are messengers, by the way, which mean the message is now different than when it was not shifted. That is just chemistry, brain chemistry. Here we go, caffeine. Caffeine is a central nervous system stimulant. So I'd ask you to know a few of these, but I think you know these already, right? You get it? Caffeine, central nervous system stimulant. Okay, increases alertness. Yeah, it keeps us awake in long drives. And there was this thing. I don't know if anybody still does it. No dose. Is the no dose still around? I don't
think
know.
you could get it, but I
No,
don't
those
think
are still a thing.
It's still a thing? Okay. When eons ago when I was in college, everybody was doing no dose. It was like, that was just, you could tell when test week came, everyone was on no dose. I didn't do no dose. I don't sleep anyway, so it didn't ever matter to me. But this is why no dose is so popular. And this is actually Red Bull and all the bulls and all the things, caffeine. This is actually also, so I need to, you moms, you can keep telling your kids this, whatever story you want to tell them, but sugar does not make them hyper. It's chocolate might because it has caffeine, but just sugar won't make them. They're happy simply because you gave them a lollipop. Okay, that's it. Okay, it wasn't the chemistry. All right, they were just happy and that got them excited about life. Okay.
Doesn't it activate the pleasure center in the brain as well?
No. It only activated it in an indirect way, yes, because you simply enjoy the taste and now you get excited. You might get excited, but it's not stimulating you to get it. It's not a direct reaction stimulate you to get it. Okay, so sugar does not make you hyper. It's a myth. Okay.
I mean, if it made kids hyper, it would make adults hyper, and it doesn't.
Yeah, I agree. I once said that at a lecture somewhere, and I was talking about science and myths of science somewhere. And this grandma in the middle of my lecture, I was talking to this big group and just really, really putting it on. She raised her hand. I said, yes. She said, son, you may know chemistry, but I'm a grandma. I know sugar. It makes them hyper. I just died. I lost it, man. I loved her doing that. Okay, here we go. The rest of the alkaloids. Let's finish this and let you out of here. Morphine, codeine, heroin, okay, oxy. I expect you to be familiar with these alkaloids, with these alkaloids. Okay, I expect you to know these names. These aren't things you'll need to know the names at this point in the semester. I don't expect you to memorize these structures. If this lecture was given early in the semester, and that is a possibility in some areas, but in this particular case today, it's later in the semester, I don't expect you to memorize the structures. But I do expect you to know the names. There you have it. We've completed chapter, what is it? 17.